So in this unit, I'm going to cover some of the data science concepts that are important for you to understand. So number one is predictive analysis. Okay, what is predictive analysis and how can you use it? Well, let me take you through the predictive analysis 101. Okay, so no one has the ability to capture and analyze data from the future. However, there is a way to predict the future using data from the past, and it's called predictive analysis. And organizations do it every day. For example, has your company developed a customer lifetime value measure that's using predictive analysis and analytics to determine how much a customer will buy from the company over time? Do you have a next best offer or product recommendation capability? That's an analytical prediction of the product or service that your customer is most likely to buy next. Have you made a forecast of next quarter's sales? Used digital marketing models to determine what ad to place on what publisher's site? All of these are forms of predictive analytics. Predictive analytics are gaining in popularity, but what do you as a product manager, not an analyst, really need to know in order to interpret results and make better decisions? How do your data scientists do what they do? By understanding a few basics, you will feel more comfortable working with and communicating with others in your organization about the results and recommendations from predictive analytics. The quantitative analysis isn't magic, but it is normally done with a lot of past data, a little statistical wizardry, and some important assumptions. Let's talk about each of these. So, number one is data. Lack of good data is the most common barrier to organizations seeking to employ predictive analytics. To make predictions about what customers will buy in the future, for example, you need to have good data on who they are buying, which may require a loyalty program or at least a lot of analysis of their credit cards, what they have bought in the past, the attributes of those products, which is attribute based. By the way, attribute based predictions are often more accurate than the people who buy this also buy this type of model. Okay, so the attributes of those products and perhaps some demographic attributes of the customer, which is like age, gender, residential location, socioeconomic status, etc. If you have multiple channels or customer touchpoints, you need to make sure that they capture data on customer purchases in the same way your previous channels did. All in all, it's a fairly tough job to create a single customer data warehouse with unique customer IDs on everyone and all past purchases customers have made through all the channels. If you have already done that, you've got an incredible asset for predictive customer analytics. Okay. The second component is the statistics. So regression analysis is the primary tool. Okay. Regression analysis in its various forms is the primary tool that organizations use for predictive analytics. It works like this in general. An analyst hypothesizes that a set of independent variables, let's say gender, income, visit to a website, are statistically correlated with the purchase of a product for a sample of customers. Okay, I'll just repeat this. An analyst hypothesizes that a set of independent variables, the gender, income, visit to website, or any other variable which are independent from each other, are statistically correlated with the purchase of a product for a sample of my customers. The analyst performs a regression analysis to see just how correlated each variable is. This usually requires some iteration to find the right combination of variables and the best model. Let's say that the analyst succeeds and finds that each variable in the model is important in explaining the product purchase, and together the variables explain a lot of variation in the product's sale. Using that regression equation, the analyst can then use the regression coefficients, which is the degree to which each variable affects the purchase behavior, to create a score predicting the likelihood of the purchases. And voila, you have created a predictive model for other customers who weren't in the sample. All you have to do is compute their score and offer the product to them if their scores exceed a certain level. It's quite likely that the high scoring customers will want to buy the product, assuming the analyst did the statistical work well and that the data were of good quality, right? So that's pretty much what regression analysis is all about. And the third The third component for predictive analysis is the assumptions. Okay, so when you're doing a statistical analysis, your regression analysis, and all, one important component is the assumptions that you're making. Okay, every model has them, and it's important to know what they are and monitor whether they are still true or not. The big assumption in predictive analytics is that the future will continue to be like the past. As Charles Duhigg, who was the author of the book The Power of Habit, a must read, he describes in his book that people establish strong patterns of behavior that they usually keep up over time. Sometimes, however, they change those behaviors and the models that were used to predict them may no longer be valid. What makes assumptions invalid? The most common reason is time. If your model was created several years ago, it may no longer accurately predict current behavior. The greater the elapsed time, the more likely customer behavior has changed. Some Netflix predictive models, for example, that were created on early internet users had to be retired because later internet users were substantially different. The pioneers were more technically focused and relatively young. Later users were essentially everyone. Another reason a predictive model's assumptions no longer be valid is if the analyst didn't include a key variable in the model, and that variable has changed substantially over time. The great and scary example here is the financial crisis of 2008 and 9. It was caused largely by invalid models predicting how likely mortgage customers were to repay their loans. The models didn't include the possibility that housing prices might stop rising, and even that they might fall. When they did start falling, it turned out that the models became poor predictors of mortgage repayment. In essence, the fact that housing prices would always rise was a hidden assumption in the models. Since faulty or obsolete assumptions can clearly bring down whole banks and even nearly whole economies, it's pretty important that they be carefully examined. Managers should always ask analysts what the key assumptions are and what would have to happen for them to no longer be valid. And both managers and analysts should continually monitor the world to see if key factors involved in assumptions might have changed over time. Even with those cautions, it's still pretty amazing that we can use analytics to predict the future. All we have to do is gather the right data, do the right type of statistical model, and be careful of our assumptions. Analytical predictions may be harder to generate than those by the crystal ball gazers, but they're usually considerably more accurate, right? With these fundamentals in mind, there are few uh, there are few important questions or good questions that you should be asking your analysts. I've covered some of them, but I'll just repeat them once again. Uh, the source, that's one important thing that you need to know. What is the source? How accurate is the data, the source of the data? How closely connected is it from with the sample data that we're talking about? If you're selling to high-end customers, but if the data has been sourced on, let's say, teenagers, or let's say uh, early 20s audience, then perhaps the results are not going to be very good predictor of my actual sales. Are there any outliers? What assumptions are behind it? And what conditions would make the assumptions invalid? The next important topic I want to talk about is correlation versus cause and effect, which is correlation is not causation, right? So the correlation is not causation. It's not necessary that things are correlated uh, and they are the cause of each other. Okay. So when is it reasonable to act on the basis of a correlation discovered in a company's data? So you picked up some data set, you did some regression analytics on top of it, and you came up with a correlation that okay, if you move the if you change the uh, age parameter by so and so, the sale of, let's say, office chairs increase, right? That is a correlation that we have discovered, but that doesn't mean that they are actually logically connected. Okay, so how do we determine that when is it reasonable to act on the basis of a correlation that you have discovered? Well, the more frequent the correlation and the lower the risk of being wrong, the more it makes sense to act based on that correlation. Just look at the diagram here. right? Uh, so benefits of action relative to cost of being wrong. So if the benefits outweigh the risk and the correlation is very frequent, okay, so there are clear causal hypothesis, right? So if there are correlation is very easily, very frequently visible, and the benefits outweigh the risk, then please act on it. But if the correlation is not so frequent, or even if it's frequent but not too many causal hypotheses, then perhaps you need to be a little more judgmental and you might need to look at your data a little more closely, right? And then finally, if the correlation is very infrequent, very unstable, so when you are running the entire model across different sample sizes for different products for different scenarios, sometimes it's correlated, sometimes it's not correlated, or the outliers have not been taken care of, and so on. In that case, again, you have to be very careful whether you would like to do this or not, whether you like to act upon the correlation that you've discovered or not, right? I will strongly recommend reading the Thomas Redman's BCG's framework. It's a fantastic article covering exactly this diagram. Uh, so, how to run data experiments? As a product manager, you will be tasked with this, or you will have to run your own data experiments at your own scale. Well, running experiments, I'll suggest that you follow the OODA loop, which is observe, orient, decide, and act. Okay, uh, which is basically you start with the question: why is our conversion rate 10% instead of 20%? Then you create a hypothesis. You create multiple hypotheses. The call to action is unclear, too many buttons on the page, page load too slowly, the value proposition is not understood, etc. Then you create experiments for each one of them. And depending on the effort versus impact of each of these experiments, you will then go ahead and start working out that what data will be needed for each one of them to prove it right or wrong, right? Uh, there's this amazing article by Simon Cast, which I'll strongly recommend for you guys to refer. The link is in the slide, so please go through it. So to conclude, predictive analysis is something that I will strongly recommend that you spend some time in understanding the tools, which is regression, most importantly. So there are a lot of other models as well, but I'll strongly recommend that don't over-index on learning every single bit of it because it's too much. Just start with regression analytics and just get used to the entire process of collecting data, cleaning the data, uh, identifying, uh, identifying and questioning the data and the assumptions, and that itself will take you decently ahead. That's it for now. See you in the next time.